Okay, let's continue. So yesterday we stopped here, and actually, yesterday we stopped here, and actually, after we discussed how to calculate the potential, electric potential due to discrete charge, then we start to consider the potential due to continuous charge distribution, and actually, similar to what we calculate the electric field, we try to cut the continuous distribution into many small packets, small charge packets, and we calculate the potential for each charge packet, and then we integrate them together. So the equation will look like this. So let's consider a practical example. So this one is potential due to continuous charge distribution. So here we have a rod, which is a charge rod, and figure A has a thin conducting rod of length L, as shown in figure B. The element of rod has a differential charge dq. dq equals lambda dx. So actually the whole yeah, we don't actually really consider the total charge. Yeah. We only consider the linear charge density is lambda. So we have dq equals lambda dx. And we consider the electric potential at point P, which is vertical distance from this rod. So which has a vertical distance from this rod, and this rod has a length of capital L, and P has a distance D from one end of the rod. So dV can be calculated as K times dq over R, and actually R is d squared plus x squared, and take the square root by Pythagorean theorem. So actually we really need to do this integration. We can subtract this term into here. Actually we want to consider the overall potential, or the total potential V generated by this charge watt. So we just integrate dV from 0 to capital L, and actually this is square root of this term. So when you learn the single variable calculus, you should be able to know how you can calculate this integral. And actually, according to a formula in appendix E, you can have the answer like this. But if you don't want to use the appendix, or you can calculate it by yourself, actually it's not so difficult. So here we can just do some simple calculation. So here we just assume x to be d tangent theta. So actually we have dx equals d secant square theta d theta. and then we can substitute it in. So the left-hand side will be equal to, well, x squared plus d squared should be this one plus d squared. So we have tangent square plus 1, which will be secant square. So which means that it will become, and then we take the square root and inverse, so it will become cosine theta. Or d secant theta in the denominator. And on the numerator, we have dx, so that it will become d secant square theta d theta. And don't forget to change the lower and upper limit, because when you substitute x equals to 0, we'll have theta equals to 0, because arctangent 0 is 0. And if we just substitute L into here, we will have, this one is theta L is, and actually theta L is arctangent d L over d. L over d. So yeah. So actually we can just cancel. We can just cancel d and one of the secant theta. So at the end, we just have a single secant theta. So you will just integrate secant theta, d theta. So we do some trick to do this integration. We just multiply the denominator and the numerator by tangent theta plus secant theta. So it become like this. So actually, we can simply have 0 secant theta L, and then in the denominator we have secant theta plus tangent theta, and in the numerator we will have d secant theta plus tangent theta, because we have d tangent theta will be secant square d theta, and d secant theta will be secant theta tangent theta. So we just do this simple trick. This one will become d tangent theta, and this one secant theta tangent theta will become d secant theta. So finally we will have ln the lateral log of secant theta plus tangent theta, and then we evaluate at theta L and 0 and subtract them. So finally, we can have something like this. Theta L, we will have L, this is D, this is theta L. So this is L squared plus D squared. So we will know that secant theta will be this side over D, and tangent theta is nothing but L over D. And you substitute 0 into this expression, it will become 0. It becomes 0 because secant 0 is 1, tangent theta is 0. So ln 1 is 0. So finally, we will have ln L squared plus D squared plus L over D. So L squared plus D squared over D is secant squared, and L over D is tangent theta, and we have Ln. So we prove this one. So next, we consider the potential due to another type of continuous charge distribution. So here we have a charge disk similar to what we have done in chapter 22. We also calculate the E field with respect to a charge disk, but now we calculate the electric potential here. So similarly, we can just separate the disk into many ring. And as you can see here, dq is nothing but the sigma times the area. So sigma is the surface charge density. So it will be equal to dr is the thickness of the ring, and 2 pi r prime is the length of the circle, of the perimeter of the circle. Not perimeter, no, not perimeter. The length, the arc length of the circle. So actually we can calculate dv is k dq r, and dq is this one. So we have sigma 2 pi r prime dr prime, and then r is this one, and also using the Pythagorean theorem, it will be equals to r prime square. So this one should be r prime. So this is r prime square plus c square, and then take the square roots, So this is dv, and we find the net potential at P by adding, or more precisely integrating all the dv from 0 to L. L, R should be R. So we integrate dv from 0 to R, and actually we can just cancel 2, and then we have 2 here, pi can be cancelled, so we have sigma 2 epsilon 0 in the front, and we have r prime dr prime, and then take the square root of this one. So this integration is easier than the previous one, because actually we can use the chain rule. So this dr prime, r prime dr prime will become dr prime square, and actually we can just add c square here because it is just a constant to the dr to the r prime. So we have this one, so that this one take the square root, and then at the denominator is just this one to the minus 1/2 power. So finally we can find the answer will look like this. So any questions? Okay, so next we consider calculating the field from the potential. So previously we know that we have an expression like this, which is which is this one, this one. So suppose we know that there is a charge or a continuous charge distribution, we should be able to calculate the E field. We should be able to calculate the E field. And given the E field, we do the line integral with respect to a defined path. So we can know that the potential difference between the final point and the initial point will look like this line integral. And actually, we don't really want to do this stuff, although the identity is like this, because calculating the E field is difficult, at least more difficult than calculating the potential. So the point for defining the electric potential here is that finding the electric potential is easier. So we try to find the potential over the whole space, and then we try to find some equation so that after we know the potential in the space, then we can use this one to calculate the E field. So you can imagine the potential is the integration although this is a line integration of the E field. So you can imagine E field should be some sort of derivative or differentiation of the electric potential. And actually it will be uh, like look like this. So here we consider we have an E field here for this point, and this charge Q0 is moving in this direction, ds and ds. So you have a work done F dot ds. This is the work done, and according to the definition for the E field, so we know that F should be Q0 times the E field. So according to the definition of the inner product, we know that it will be Q0e cosine theta ds, which is theta is the angle between the E field and ds. So the right hand side will look like this, and the left hand side F FDS will be what? So FDS will be nothing but minus Q0 dB because it is the potential. So it has a negative sign here. So actually Q0 and Q0 can be cancelled, and we have E cosine theta and ds. We just divide it on both sides. So E cosine theta will be negative dv ds. So it's a one-dimensional expression on this s-axis. So we have es is the projection of the E on the s-axis. So we have es equals to negative dv ds. Suppose it is moving along a single direction. So it is a derivative. So if we can find the voltage, the electric potential, and then we take the derivative with respect to the space. Here is a s direction, and then we have a minus sign. So it will be the magnitude of E on this axis. So more generally, if we consider it in a Cartesian coordinate, which means a three-dimensional space, so we will have dv dx minus dv dx will be the x component of the E view, and E dy will be minus dv dy, EZ will be minus dv dz. And actually, mathematically, we will write it like this. So E, the vector E, which is the E view, will be the negative gradient of V. We call this the gradient. 中文叫做梯度。This is called a gradient. Actually, we can write a gradient using the unit vector, so it will look like the partial x in the x direction plus partial y in the y direction, which is j hat, and plus partial z in the z direction, which is k hat. So sometimes we write it like this, So this is a gradient. 它正确的名字叫做梯度，有时候我们就会叫它做倒三角。So just in the previous slides, we know that v will be negative, the line integral of E over a path, and then we can write that actually this is equivalent to this one. So it's just like the fundamental theorem of calculus. When you learn the single variable calculus, you know that. So suppose you have a function capital F of x. If you just take the derivative with respect to x, so it will become small f of x. So it will become so actually a x f x prime dx should be this one. So this is what we call the fundamental theorem of calculus for the single variable case. And now, so this is called the fundamental theorem of calculus. So this is a single variable case, and now we have this one will become in high dimensional. So we will have gradient v minus will be E. And for this one, we will have v will be negative E dot ds. It's just actually the same stuff. So you can check it on Wikipedia if you are interested. So in Wikipedia, it's called the gradient theorem. So the gradient theorem, also known as the fundamental theorem of calculus for line integral, says that a line integral through a gradient view can be evaluated by evaluating the original scalar view at the end of the curve. Which means that if we can find the electric potential over the space, and then we take the gradient, which is actually this one. We take the partial derivative with respect to x, y, z direction, and then this one is the x uh, x component, and this one is the y component. This one is the z component. So it will look like this. So actually, E can be written as negative partial v partial x in the x-axis, negative partial v partial y in the y-axis, and partial v partial c in the z-axis. So I think these stuff are very interesting. So maybe I think we can finish this one. So here, an electric potential at any point on the central axis of a uniform charge disk is given by this one. We just derive it a few minutes ago. So starting with this expression, derive an expression for the electric field at any point on the axis of the disk. Yeah. So we just simply make use of this one, or more precisely, only this one is sufficient. This one is mathematically correct, but for this course, you may not really need to know much about it. Actually, this is nothing but a single variable differentiation. So actually, v is nothing but a function of z. So we know that. So we know that Ez, which is the z component of the E view, is nothing but negative dv dz, because it is only a function of z, so that we can just replace this partial into a d. So here, calculating this derivative is quite simple, because it is nothing but negative sigma over 2 epsilon naught. And for this one, you need to use the chain rule. So it will become 1/2 square root of c square c square plus r square, and then you take the chain rule, which will be 2z, and then this one minus c will become negative 1. Minus c will become negative 1. So negative 1. So finally, 2 and 2 can be cancelled. So finally, we can distribute the minus sign into here and here. So finally, we can write it as sigma over 2 epsilon naught 1 minus z over square root of z squared plus r squared. So actually, we have derived it in chapter 22. We've derived it in chapter 22. So actually, at that time, we need to consider a ring, and then we calculate dE for every ring and integrate them together. It may be more difficult because you need to consider the y-axis component, and then you just cancel them, and then you need to consider the z-axis component, and then you integrate them together. So you need to consider something like some uh, cosine cosine theta, something like that. But here, consider the potential, electric potential is easier, so that in here we can calculate this expression easily, and finally we can just take this derivative, and then we can know the z component of the electric field. So that's why we need to learn the electric potential in this chapter.